I will begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you'd encourage them as they work on this course, just to give them energy each day to carry on. Just remember, Lord, that whatever we do, we should do for you, Lord. In your name I pray. Amen. Okay, so I will start class with just a couple of loose ends. So the first loose end was an example that I meant to do. So if we think about the real numbers, all right, as a vector space over the rational numbers, this is kind of an interesting example. Do the real numbers form a vector space over the rational numbers? In other words, can you check, is that actually a legitimate vector space? If I think this is my V, so to speak, right, and this is I usually used an F in the generic setup. If you sort through it, I think it makes sense, right? So if you take the sum of real numbers, real numbers are definitely closed under addition. They got 0, additive inverses, so the additive structure of the real numbers is all good. How about the if I check like a rational number C times the sum of two real numbers, is that equal to Cx plus Cy? Yeah, right? And all the other axioms you need for scalar multiplication make sense. So in fact, yeah, the real numbers are a vector space over the rationals. Then you can ask the question, what's the dimension? What's the dimension? The rational dimension, if you will, of the reals over the rationals. In contrast, the dimension of the reals over the reals, right? If I think of the reals as a real vector space, well, the dimension is 1. Why? Because the real span of the number 1 is what? That's C times 1 such that C is a real number, which is, stupidly, C such that C is a real number, which is a lot of writing for this, yeah? So any field, in fact, is a vector space over itself with dimension 1. But what's the dimension of the reals over the rationals? Let me point out to you the following subspace. Here's a subspace. We could look at W, the span of, I don't know, let's say square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, square root of 13, square root of 17, square root of 19, and you get the idea. If you play around with this, it's fairly obvious that that's a linearly independent set, in the sense that if I take, any like C1 times root 2 plus C2 times root 3, etc., if I set that equal to 0 for C1 and C2 in Q, right, that implies that both C1 and C2 are 0. If you had a non-zero solution, that would imply that the square root of 2 or the square root of 3 or both of them were rational numbers, which is just not true. So it's kind of like a typical Math 200 starting proof kind of question. I'm not going to go into the details here, it's not really the point. My point to you is that is in fact a linearly independent subset, right? And here I'm talking about the rational span, which means I take coefficients from Q. So what's the dimension of the reals over the rationals? It's infinite, yeah. So you say, you mean to tell me that the reals are one-dimensional as a real vector space, but they're infinite dimensional as a rational vector space? Yes, I mean to tell you that. Dimension very strongly depends on your base field, because the spans that are involved are based on your choice of scalar. And changing the choice of scalar can change something finite dimensional into something infinite dimensional. This example shows that. So that's kind of a curious thing. So that was the major loose end, I think, from my previous lecture. So now I want to talk about something a little bit more concrete, is how to calculate the coordinate vector, let's say v beta, for beta v1, v2, vk, a non-standard and we could go to n, non-standard basis for Rn. So, how do you calculate the coordinate vector for with respect to a non-standard basis? Like, how do you actually do that calculation? What's a good way to do it? So, basically, the question then is, we take a vector, let's say v, right? And we can write that as what? We can write that as something like x1 v1 plus x2 v2. Well, you know what? Let me pick let me change my letter choices here. I don't want to use v for the variable vector and for the basis vectors. That's a little bit confusing. Let's switch this v out for an x. All right. And so just to make sure that you don't have any kind of preconceived notions about my letters, let's say that x is equal to c1 v1 plus c2 v2 plus plus cn vn, where beta v1 v2 vn is basis for Rn. Now, what's that mean? What does it mean to say that beta is a basis for Rn? What does that tell you about that set beta? Linearly independent, and what else does it do? It spans, right? It's linearly independent spanning set. So, I'm assuming we're looking at some point x, some vector in Rn, and I'm writing it like this. And now if that's the case, then by definition what? What's the coordinate vector of x with respect to the beta basis if this is true? Yeah, it's c1, c2, cn, right? That's the coordinate vector of x with respect to that possibly non-standard basis. Right? I mean, in the case that beta is the standard basis, x beta is just equal to x again, right? By the way, beta equal to e1, e2, en gives the coordinate vector with respect to that basis just equal to x again. That's the standard basis. Okay, so question, guys. What is this equation? Because what's our goal here? Solve for C1, C2, Cn, right? Hey, that's your backpack, not the trash can. Oh well. It's like I thought that was yeah. So what is this here? Can you rewrite it? Thanks. Much appreciated. I've been trying to hit Ian in Calculus 3 all semester. So far, I still haven't hit him. He always sits there. I'm trying to hit him. I was trying to hit you, but
That's Sprano, so I'm used to being thrown up more.
Ah, so you like to sleep in class. All right, so very good. So C1.
I always stay awake.
You stay. Oh, you stayed awake. So you must.
Tell me for the people that stay.
So did you say something offensive then? I mean, like usually we'll throw a marker at if you say something wrong, right? Or somebody just throw it for fun, or I mean. For practice. So you had a standing agreement with Sprano about this. Huh, I like it. See, my father claims that he had some kind of standing agreement with his differential equations professor that he would give him and my dad and another student like answers to prearranged questions that they would answer during class to intimidate the other students. And that if he did this and And he came to all the classes that he would pass because my dad was not a very strong math major, and so he really needed to pass his class. So the professor came to some kind of arrangement with him and the other student in the interest of messing with the other students. Now, if this is actually a true story, it's fantastic, but I don't know. I wasn't there. Now, so these are vectors, right? Vector, 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 constants. We can rewrite this as what? This is really just v1, v2, vn times the vector c1, c2, cn, right? Equal to x. And, x you could write as, I'm just going to write it as x, but of course x, we could write as x1 through xn, right? I mean, we have this notation, right? Those are the usual Cartesian components of x with respect to the standard basis. How do you solve that for c? Now let's give this thing a name, right? This is the matrix of the basis, right? Beta bracket. How do you solve for c? Let me rewrite it again. We have matrix of beta times the c vector equals to the x. Or better yet, that's not the c vector. We have another notation for that already. What is it? C vector is the coordinate vector of x, right? With respect to the beta basis equals to x. That's what this equation says. See, because this is the coordinate vector of x with respect to the beta basis. So how do you calculate the coordinate vector, x of beta? Surely someone here knows how. Multiply by the inverse. Oh, multiply by the inverse. Okay, very good, very good. Okay, so yes, thank you. So yes, multiply by. Now, why can I do that? How do I know that inverse exists? Well, I just assume linear independence of that, right? It's an n by n matrix made with linearly independent column vectors. So by our previous discussion about invertible matrices, we know that's invertible. It's got non-zero determinant. Its inverse exists. In fact, we know how to calculate the inverse if we want, right? So there you go. X beta is equal to beta inverse times x. There you go. That's a nice formula for calculating the coordinate vector of a given vector with respect to a non-standard basis. What happens to that formula when we take beta to be the standard basis? What's in this context up here, what's the matrix of the standard? What's the standard matrix basis? It's what? I heard you. It's I, yeah. So that simplifies to the, right? Yeah? All right. Let's do an actual example. How about this? Beta equal to 1, 1, 0, 0, 1, 2, and 0, 3, 0. There's my basis, beta, and I want to find the coordinate vector of the vector, let's say, 1, 15, 4. So I'm not actually going to do what I just did over here because this is like, how do you, all right guys, this is a nice symbolic, summary of how we would do it, right? But for actual numbers, do you want to calculate the inverse? No. To solve this system, what do? We're looking to solve what? We're looking to solve C1 times 1, 1, 0 plus C2 times 0, 1, 2 plus C3 times 0, 3, 0 equal to what? 1, 15, 4, right? The C1, C2, C3 are the coordinates that we're looking for. right? So I don't know about you, but the way I solve that is to put it in a matrix 1, 1, 0, 0, 1, 2, 0, 3, 0, and then my inhomogeneous term, 1, 15, 4, right? Now, symbolically, what is that? That's the basis matrix beta concatenated with what? The 1, 15, 4, right? I don't really need to write what I just wrote on the left-hand side. I'm just saying it's the basis matrix concatenated with the vector you're trying to find the coordinates of, right? And you do some row operations, and after a while, you get 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 2, 3 over here. Which incidentally proves something while I'm at it. It proves that my beta actually was a basis, right? Because we get the row reduction of it to be identity, which speaks to the linear independence of beta. So it's in fact a linearly independent spanning set. Anyway, so what's that?
That bottom 3 at the end of the augmented coefficient matrix, wouldn't that be a 4?
No, it's a 3. What do you mean?
So
This 1, 15, 4 is coming from this.
right,
0, 3, 0, 0, 1, 2, 1, 1, 0.
right. So I'm just trying to make sure if I did an issue with, I was going through the operations of the coefficient matrix and I ended up with 4.
Well, we can see if I'm right or wrong, right? So 1 times 1, 1, 0, plus 2 times 0, 1, 2. I mean, it's possible. I made a mistake. Plus 3 times 0, 3, 0. If I'm right, we should get 1, 15, 4, right? Because that's what this means for that to be. So what I'm claiming was the coordinate vector of, I said it in words, I didn't write it out yet, 1, 15, 4 with respect to the beta basis is 1, 2, 3. Is that true? See, I get 1, right? 1 times 1 is 1. 1 plus 2 is 3. 3 plus 9 is 15.
Okay, I can remember the being wrong.
0 plus 4 plus 0 is 4. So I didn't actually do the row reduction. I know that's how the row reduction works out because that's how I made up that vector. I took 1 times the first thing in the basis, 2 times the second, 3 times the third, because I know that then that's how the row reduction will work out. Yep. Ah, curses. Well, there's only one way to fix this problem then. 3 plus 9 is not 15. Thank you. Very good. 3 plus 9 is 12. There we go. So we can both be wrong. You're probably right.
I was up till 4, so
You're up till 4?
I was up till 4 last night.
Oh. Is that it? I mean, that's all? Just 4?
I'm a newbie.
Oh, you're a newbie. Yeah, I don't usually survive that long anymore. 1, 12, 4, 1, 12, 4. There, I think I fixed it. Thank you, Taylor. Much appreciated. So arithmetic, my old nemesis, yes. Now, does this calculation here, does it matter that it's 3 vectors in 3 dimensions? I mean, what if I was calculating the coordinates of, you have a homework problem which is based on a 3-dimensional subspace of a 4-dimension in R4, right? So there, a very similar calculation would still make sense in that example, right? But you couldn't actually, you couldn't do this in that example, I suppose, because it, well, let me just, So all I'm trying to tell you guys at the moment is that you can calculate coordinates with respect to non-standard bases in Rn using the calculational skills that we've already acquired in the first third of the course, right? So I'll let the homework say the rest about that. So that brings us to continuing our study of dimension. In particular, I want to talk about proposition 6.6.5. Now, if you want to be picky, we already proved this we proved this proposition in a different way last class, but I want to show you a separate and rather different argument today, okay? Again, I'm after a proof, a demonstration that the number of vectors in the basis for a finite dimensional vector space is fixed. It's invariant. It doesn't matter if you have a set of 4 vectors that is a linearly independent spanning set for a for a vector space, then any other basis for that vector space will also have 4 vectors. So the number of vectors in a basis is an invariant of the vector space, which of course we defined to be dimension last time, right? So here's the proposition V. So what's the difference here is today I'm going to give you a constructive proof of it, okay? Last time we proved by contradiction. This time I'm going to give you a constructive proof. Let V be a vector space over F, over a field F, all right? And B, B1, B2, Bn basis of V. Then any other basis of V also has n elements. Right. In other words, two finite linearly independent generating sets for a vector space must have the same number of elements. Okay. So last time I told you guys this theorem that if we had a spanning set with n things, and then we took m things where m was larger than n, that necessarily was linearly dependent. I didn't prove that. We used that to find a contradiction, right? So here I'm going to give you a rather different argument. But I think it's useful. So let's suppose, here's the proof. Suppose that B is, as stated there, B1 through Bn basis for V. And let's also suppose that F, which has got F1, F2, F, let's say sub P, is also a basis for V. Right? But I'm not, at the start of it, assuming that P equals to n. Right? What's our goal? Our goal is to show P equals to n. All right? So what do we do? Well, observe that the kth element of B is an element of the span of F, right? Thus, there exist constants, right, in the field. Let's say C1k, C2k, How many things in F? P, right? CPK in the field, such that what? Such that BK is equal to a sum, I equals 1 to P of C, I, K, F sub I. Right? But what else do we have? F sub I is an element of what? The span of what? How about B, right? Thus, there exists what? D, 1J, 1I, yeah, thank you. D, 2I, D, how many? Ni in F, such that F sub I is equal to a sum let's use j this time. J equals 1 to n of d j I b sub j. Right? Hence, what we actually have is that b sub k, right, is equal to the sum I equals 1 to p, Cik, sum, let's see here, my f sub I is actually sum j equals 1 to n, right, of d ji bj, right, which by properties of the vector space and finite sums, we can rewrite as the sum I equals 1 to p, the sum j equals 1 to n. Actually, I'm going to put the I sum inside. I'm going to switch the order of the sums. I equals 1 to p. Put the j on the outside, actually. J equals 1 to n, right? And this is going to give me C, I, K, D. And I'm actually going to reverse the order of the coefficients even because I'm looking forward. I mean, these are constants in the field. They commute, right? So this is D, J, I, C, I, K, parentheses, B sub j, right? And on the other side, we could also write this as the sum, j equals 1 to n, of Kronecker delta, jk, bj. We put it consequently in here. There you go. I've told you guys about how we can use Kronecker deltas to kill sums. I didn't tell you about how we can use them to create them, but we can. The reason I'm doing that is just to point out to you that b sub j is a basis, right? b1 through bn is a basis, which means it's linearly independent, which means by your homework question, we can equate coefficients, right? So equating the coefficient of b sub j, what's it tell me? We get delta jk is equal to the sum I equals 1 to p of d ji cik, right? But what is that? In other words, I mean, this is equal to the matrix D, the matrix C, the jkth components of it, right? And this, of course, is the jkth components of the identity matrix, right? If you allow me that small manga style comment. So, therefore, dc is equal to I. And I maybe should put an I sub what? J and k are free to range over what range here? Which kind of identity matrix is that? J and k are both ranging over what? J ranges from 1 to n. How about k? K is an arbitrary thing in B, right? K also ranges from 1 to n. J and k both range from 1 to n. That makes that an I sub n. That's the n by n identity matrix, right? You guys follow? Well, likewise, you can prove that C times D is equal to I sub p. Just switching the roles of the bases, the argument's completely symmetrical, right? So going through the same argument, just interchanging the roles of the two bases, we get that. C times D is equal to I sub P. Right? Now your homework question. Your homework question, you have proved in your homework that the trace of the product of two matrices is equal to the trace of the two matrices in the opposite order. So trace of CD is equal to trace of DC, which in this context tells us that the trace of the n by n identity matrix, I was about to write trans, that's something else. So your trace of IN, trace of IP, but what's that say? That says n is equal to p. There you go. A direct proof that the size of two bases have to be equal by just straight computation. So we don't need contradiction. Contradiction makes the proof easier, sure. But we don't need contradiction here. We can just prove it directly, and that's what I just did. Any questions? That's part of the reason I had that homework question about the trace, is so that you understand that, yeah.
How do you get from what's on the right on the second line to having an arc or delta?
Oh, here to here?
Yes.
Well, you can go back from here to here, right? This is 0, except in the case j equals to k. So I'm just adding 0, n minus 1 times. This simplifies to that. So that's why they're equal. Because this is only 1 when j is equal to k. So this becomes delta kk bk, which is just that. Because delta kk is 1. Yeah. But that's a weird step, I know. Yeah. Okay, so yay. So anyway, next on our agenda is a lemma. This one is not in the notes. The notes dance around this idea. I think this lemma is proved in a proof somewhere. Oh, by the way, guys, before I forget, proposition 6.4.3 in the notes. I have this comment for you. The proof is on drugs. All right, and not the good kind either. I'm sorry. As I was telling you in office hours before, all drugs are bad. Don't do drugs, except coffee. So yes, no, the proof of proposition 6.43 as it's currently written in the notes is just horribly mangled. I need to fix it. I will fix it and repost the notes for you guys, okay? But this brings up an important point. You should be studying the notes, right? You should be trying to understand proofs in the notes, right? I don't even have another. So in the past, students have complained, we have the notes, we have a textbook. There's too much. I eliminated the textbook. There's only the notes. You should have time to read them. You should also have time to think through them. Well, you should find time to do that. That's the best way to succeed in here. So when you come across something that is just insane, like the proof of proposition 6.43, what is the proper action? Sit on my hands, remember this for course evaluations. Professor wrote notes, don't make any sense. Arr. No, you email me. You say, Dr. Cook or James or whatever it is you want to call me. This is insane. What are you doing? This makes no sense to me. And I will say, well, it makes sense. You know, you need to blah, blah, blah. Or I'll say, yes, you're right. It is totally garbage. And let's fix it. And, you know, I did have these proofread by somebody who knows much more than I do last year. But, you know, that doesn't mean everything has been found. And I wasn't talking about Sam's step. So, anyway. Okay, so although Sam does certainly know more than I do about computer science, heavens knows. Let's see here, because I know nothing. Anyway, I'll shut up. Let me stop digging this hole. Lemma. This lemma is not in the notes. So this lemma is important, though. It's a core concept of coordinate vectors. And the lemma says this. For a finite dimensional vector space V over a field F with basis beta, let's say, we have for any x, x and y in V, well, actually, let's be greedier. let's be greedier. For any x1, x2, x sub k in V, and c1, c2, ck in F, right? We have the following. The coordinate vector of c1x1, c2x2, plus ckxk, right? The coordinate vector of that with respect to the beta basis is, guess what? Poor planning on my part, sorry. C1, coordinate vector of the first vector, plus C2, coordinate vector of the second vector, plus CK, coordinate vector of the kth vector. Which we could write much more succinctly and perhaps better as saying that the sum I equals 1 to k of ckxk is the sum, the coordinate vector of that is the coordinate vector, is the linear combination of these guys. Let's see here. Let me put it into words. The coordinate vector of a linear combination is the same linear combination of the coordinate vectors. How would we prove this? I'll just do the proof for k equals to 2, since I'm probably short on time by now. If we look at, suppose we got x and y, and I'll use x and y for vectors in V, right? And C1 and C2 for scalars in the field. So we're assuming what? X is equal to? Something like, I need some letters for constants. Let's see. I don't know. Lack of imagination here. I've used all my letters. I don't know. How about A1? I need to pick a basis, right? Beta is V1 through Vn again. So I'm saying x can be written as the sum I equals 1 to n of, let's say, b sub I, v sub I, right? And y is equal to the sum I equals 1 to n of letters, d sub I, v sub I, right? In other words, the coordinate vector of x with respect to the beta basis is what? What's the coordinate vector of y with respect to the beta basis? It's the b's or it's the d's. So if we take, you know, C1x plus C2y, what's that give us? You can work it out. It's going to be the sum I equals 1 to n of C1bi plus C2di vi. I'm just skipping a little bit details here, but you can easily work that out by just combining the sums and bringing the scalar multiples inside the sums, using the properties of vector space that we can do that. Yeah. But of course, this shows that the coordinate vector of C1x plus C2y is what? Right? It's the ith component of it, let's say. The ith component of that is CBI plus C1bi plus C2di, which, by the way, is the ith coordinate vector of C times the x beta, C1x beta plus C2y beta I. But that holds for I equals 1 to n, right? So that proves the lemma for the case k equals to 2. And if you can do it for 2, you can bootstrap your way up to doing it for k things just the same. Right? It's easy to see how to get from 2 to 3 and so forth, 3 to 4. This sounds like an induction proof if it was done formally. Right? So you're like, well, this is, so what? I mean, what does this lemma do for us? Well, how about this? It gives us proposition 666. Let's see here. Sorry. I'm a little too giddy about that. It's actually not an evil proposition. It's a good proposition. It's, I know. So proposition 6.66, it says, suppose V is vector space with the dimension of V equals to n, all right? Then a couple things we can say from that. Number 1, if S is a subset of V and the number of vectors in S is greater than n, then S is what? So can you fill in the blank? Do you guys understand? What should go there? Yes, linearly dependent. So what would a proof of this look like? How about this? We let S equal to, S1, S2, Sk, right? This is a subset of V. These do not have to be column vectors, right? These could be matrices or polynomials or all the kinds of other things we've talked about. They're abstract vectors, a set of k abstract vectors. Let's assume that the dimension of V is what? N, all right? So what you can do then is consider the set of coordinate vectors with respect to S, right? So consider the set S1 beta, S1 beta, S2 beta, Sk, the coordinate vectors, right? This is a subset of Rn, given beta equal to V1, Vn. This is my basis for V. Now, how do I know a basis exists for V with n things? I'm assuming that in this proposition, right? I'm assuming that V is an n-dimensional vector space. That is to assume that there exists a linearly independent spanning set with n things in it. Let's call that thing beta, right? So with respect to beta, I can look at this set of coordinate vectors. Coordinate vectors are what, though? They're column vectors, right? So this thing, right? What can I do with that? I can look at, consider the matrix, right? I can consider the matrix S1 beta, S2 beta, Sk beta, right? I can consider this matrix, right? That's an element of what? R blank by blank. How many rows? How many columns in this matrix? I think it's got k columns, right? How many rows? each vector is an n vector, right? Because an n-dimensional space has an n-dimensional column, n-dimensional coordinate vector. So this is an n by k matrix, right? What's the maximum number of pivots that this matrix can have? The number of rows, right? So this matrix can have at most n pivots, right? What's the least number of pivots it can have? Well, maybe that's the wrong thing to say. How to say this? Oh, words. Well, let's think about the first case. Now think about number 1. What if the number of things in S is larger than n? What's that say? The number of S is, by the way, what I'm calling k, right? If the number of things in S, k, is greater than n, I need to give this matrix a name. Let's call it M, all right? Then what can we say about M? Up. M has a non-pivot column, right? At least one. Let me put it in less sort of daunting terms for you. If we were working in a 4-dimensional space and I had a set of 5 vectors, when you look at the coordinate vectors and you reduce them, you're looking at a 4x5 matrix, right? A 4x5 matrix has at most 4 linearly independent columns, right? Because there's at most 4 pivots. And then anything that's not a pivot, you can build from linear dependence of the pivots. Same is true here. If I have more columns than rows, that means I have at least one non-pivot column. And consequently, that means I have a linear dependence between the non-pivot columns and the pivot columns, right? But then, if there's a linear dependence between the coordinate vectors, and you have this lemma, you can, and this is, by the way, an if and only if thing too, by the way. I mean, this is an equality, right? So if I have a linear dependence amongst the coordinate vectors, it will imply a corresponding linear dependence between the, in the original vector space, right? If these are equal to 0, that means that the coordinate vector of that vector is 0. But the only way you can have the coordinate vector of a vector being 0 is if it's the 0 vector. So any kind of linear dependence in the coordinate vectors transfers back to the same linear dependence in the vector space itself. So studying the matrix of the coordinate vectors gives me information about possible linear dependences in the original vector space. So in particular, more than one pivot column, which then says that the set of coordinate vectors are linearly dependent. Then following from the lemma, S is linearly dependent. On the other hand, if you had a subset of V, right, with less than n vectors, then you have the number of S equals to k to be less than n, right? And if you think about that, that means that, for example, it could be something like this. No, I can't. I'm sorry. Stop that. Well, anyway, if k is less than n, it follows that you can't span everything in Rn with those coordinate vectors from S. And then tracking back, that means there are things in vector space V that you can't span as well. So anyway, this proposition does, yes, this gives us a nice theoretical result, right? But it's more than that. This proof actually gives you a template for how to attack more complicated questions of linear independence in abstract vector spaces, right? You can trade your abstract question for a corresponding coordinate vector question, solve that using techniques of the first part of the course, and then the lemma allows us to track back and make concrete statements. What you can't do in here is do that without telling me you're doing it. And that's the thing you guys tend to do. All right? You actually have to tell me, I'm picking a basis, I'm looking at coordinate vectors, and you have to explain that. It's like you can't just in a fuzzy way do that. You must be precise. All right. Well, sadness. Well, what we were about to get to is your basic sort of intuitive theorems of the course, and these are kind of big ones. Proposition 6.67 that says that if we have a basis for a subspace, we can extend it to a basis for the whole vector space. Proposition 6.68 says that if we have a non-empty subset of a vector space and if it's linearly independent, then if we pick V outside the span and adjoin it to S, then it's still going to be linearly independent. So if you want to enlarge a linearly independent set, what you do is you pick vectors outside the span of it. It's kind of common sense, right? And then the other part of 6.68 says that if you have a if you remove a vector from a generating set, it gives you the same span only if that vector you removed was already in the span. Kind of like duh. But anyway, the theorems that I'll try to write those down next time. But the rest of section 6.6 kind of gives you the central basis building propositions that guide our thinking going forward. But we're pretty much done with 6.6, and I think the next thing on the schedule is what? What comes past? What's next? A test? I think we have, I think next up is linear transformations. Is that right? I can't see, but anyway, you guys go. Listen to me for.